this isn't going to be a problem. This is just going to be an explanation that we talked about in class regarding angular momentum. And we talked earlier in the year about regular momentum, and we had a formula for that. It was P equals M times V, where P was our momentum, M was our mass, and V was our velocity. So again, we would call that, in air quotes, regular momentum. And if you think about this, it has two parts. It's got mass, and mass is really a measure of inertia. Obviously, we can use it for other things, but it tells us the ability of our object to resist changes in its state of motion. And this is a linear velocity. So I guess you could say this is, instead of regular momentum, linear momentum. And then we had a discussion also where we talked about hoops and spheres and discs and balls and planks and various other things that had a whole variety of formulas for the rotational inertia. And depending upon how the mass was distributed and whether it was a shell or a sphere or a solid disk, they all had these different things, but they were represented by this concept of rotational inertia, which was an I. Well, we've got linear inertia, but we've also got rotational inertia. So we're just going to substitute in a little bit here, and we're also going to have angular momentum, which we represent with an L. And the formula for this is going to be that angular momentum is equal to angular momentum, or rotational momentum, is going to have the rotational inertia, I, but instead of regular velocity, because it's angular or rotational, we're also going to have rotational or angular velocity. So we just have the two formulas, and just like all the other formulas where we could plug in rotational variables instead of linear, we have this corresponding thing. If linear momentum is inertia times linear velocity, then angular momentum is rotational inertia times rotational velocity. So there's our little corresponding setup. Let's take it one step further. When we were working through collisions with momentum, we had this idea where if one cart slammed into another, that was our before, and we stopped this cart, and then the next cart, again, not to scale here, I'm running out of paper, that cart takes off. We knew that momentum was conserved in this collision because this mass and this velocity, and this mass and this velocity added up to a certain amount of momentum. And if we did the same calculation for these two carts, it was the same. We have the same thing with rotational inertia. So was linear, it was something like mass 1, velocity 1 equals mass 2, velocity 2, right? This cart's momentum had to equal that cart's momentum. A little more complicated version would be the m1 v1 plus m2 v2 equals, and these would be initially, get rid of that, then it would be m1 v1 final plus m2 v2 final. It was all conserved. Well, let's go ahead and write this where we've got angular momentum. So it would be I omega. So this would be initially and finally. And this is that demonstration where we sat in the chair and held my arms in with the dumbbells, or one of you, and we spun the chair. And then as we moved the dumbbells out, that moved the mass from being in the center outward. And as that radius got bigger, the rotational inertia got bigger. And so if this goes up, in order to keep this constant, my angular velocity had to go down. So during the demo, you saw that when the arms went out, the rotational inertia went up and the angular velocity went down. And if we had had a good enough chair with really good bearings on it and it kept spinning, you can pull the arms back in, the radius comes back down. So that means when this goes down, the angular velocity would go back to what it was originally. So there's your reminder discussion of conservation of angular momentum.